All right. Well, we'll take in the middle. All right. So today, chapter 13. Here we.
I thought I liked the one-day chapter.
No, it'll be more than one.
All right, cool. 4 days.
Probably 2 or 3.
Damn. And then another test.
Yeah. Yeah.
That's actually good. What are you talking about? Let's veer away from that foul language.
You know, this is the way you should look at it. This is the way you should look at it. In a math class, if it's quick in between the tests, what does that tell you?
What?
If it's fast in between the tests, what does that tell you?
Easy.
It should be like a doable amount of material, right? If it's a long time in between tests, then you have a lot of material. That makes life harder, right? More stuff to study. You should be wanting like quick turnaround between tests. I mean, it's a test, so like whatever, but you know. All right. So today we're going to continue talking about polynomials. We're going to start by talking about graphs of polynomials. And there are 2 key features on the graphs of a polynomial that we're going to start by talking about today. Those are the extrema and the zeros. So the extrema for a graph are the relative high or low points, right? And the zeros are where the graph crosses the x-axis. So let's say we have the function x cubed minus x, and we want to locate the zeros and the extrema for this function. To do this, we are going to use our calculator. If you have a calculator with you, I invite you to take it out to follow along. Sure, go ahead.
Thank you. They said you wanted to charge.
No? You said you don't want it charged.
No, didn't know we were still in second grade.
I thought I was just gonna help you out. It's fine if you don't want to charge, you don't want to charge.
All right. So we're going to start by pressing the y equals button up in that upper left-hand corner. Y equals. And then we're going to type in our function just like it looks on our sheet of paper. So x cubed minus x. And to graph this now, we've been monkeying around with our window all last chapter, right? We did a whole bunch of zoom stats probably. So to graph this, I'm going to press the zoom button there on the top row and pick Z standard just to reset my window back to something probably sensible. So if I'm looking at the relative high and low points and the x-intercepts, everything I care about is right in here, right? Everybody agree? I don't have a great picture of that, though, because it's awful far away, right? So I'm going to reset my window here so it just includes the part of the graph that I'm really interested in. It looks like over here, that looks like about -2 on the x-axis, and that's probably about +2. And that looks like about -2 on the y-axis, and that looks like about +2. So I'm going to reset, I'm going to press my window button. And I'm going to just change the x min and x max to be -2 and 2. And the y min and y max to be -2 and 2. You could have also done like a zoom in. I like doing it this way because I like having a little bit more control over exactly what my window size is going to be. But if I do that and hit graph, that gives me a much better picture of the parts that I cared about, right? Everybody's cool? All right. Let's find those extrema first. If I look at the graph, how many extrema do you guys see? What? How many extrema do we see? 2. Great. So one of them is here, right?
Yep.
What is that extrema called? Okay, it's a maximum, but there's 2 kinds of maximums. That's a local max. Very good. So let's find the point where that local max occurs. To do that with our calculator, we're going to press second and then the trace button. And which command sounds like the one that we want? Maximum. So the calculator is going to ask for 3 things from me. Notice at the bottom it has left bound with a question mark. So what I'm going to do is I'm going to use the left arrow button on my calculator to move my cursor so that it's left of where I think that maximum is. So that looks fine there. I'll press enter. Now it asks for right bound. So again, I'm going to use my right arrow button to move my cursor somewhere where it's right of where I think that maximum is. That looks good. I'll press enter. And then the guess, as long as there's just one extrema in between your left bound and right bound, your guess doesn't really matter. So I'm just going to press enter again. And I get negative 0.577, comma, positive 0.385.
Not the global max as well,
It is not a global max. Let me go bring that back up in a second. We'll talk about why it's not a global maximum. So do you see any points on this function that are higher than that point?
Yeah, but they don't have a peak.
Well, that doesn't matter. That's why it's only local. Because in this little area around it, it's the highest spot, but it's not the highest spot for the entire graph. Does that feel okay? Because like, say for instance, this point right here, it has a bigger y value than our point we just found. So it can't be the global max because there's lots of points that have bigger y values than that one. You know what I'm saying? But there's not a one point that has that's bigger than or equal to all of the points because it's going up forever, right? So there's no global max here. All right, use your calculator. Try to get the local minimum now. Try that on your own. Use your calculator. Try to get the local minimum. I'll write the answer down so you can check. But do that on your own. We did this first semester, so you should kind of remember still how to do this, especially after I reminded you where the menus are to get to the commands you need. But this isn't too hard, right? Who got the right answer? Good job, Will. Good job, Jacob. Everyone have a chance that was trying to do it? Okay. Now let's find those zeros. So remember, the zeros are the same as the x-intercepts. How many zeros do you see on this graph? 3, right? I have 1 right there, 1 right there, and 1 right there. Everybody agree? Let's use the calculator to find the location of those zeros. I'll press second and then the trace button. These commands, which one sounds like the one we want? The 0 command, very good. It's going to ask us the same 3 questions. So I'm going to find this 0 first. So I'm going to move my cursor using the left arrows to be on the left side of the 0, so that looks good. I'll press enter. And then I'll move my cursor somewhere to the right of the 0, press enter. And as long as there's only 1 0 in between those left and right bounds I chose, my guess doesn't matter, so I'll just press enter, and I get x equals -1. Everybody's cool? Try to find the other two. I'm going to write down the answers on the board so you can check them as you go. But take a minute and try to find at least one of them. After you've done one, I suppose you probably don't need to do the third one if you didn't want to. Because I feel like we've done this before, and once you got it, you kind of got it. It's not too hard. You guys feeling okay on this? Pretty easy. You kind of remember this from first semester, I hope. The calculator pieces anyways. So notice in this previous problem, or this problem we just got done working on, that we saw we had 2 extrema and 3 zeros, right? It's possible to predict how many of those things we should have to some extent just by looking at the function. So that brings this following theorem. This says that a polynomial function of degree n will have at most n zeros and at most n minus 1 extrema. So in the example we just did, what was the degree that we had? 3. How many zeros did we find? 3. How many extrema did we find? 2. 3 minus 1. Everybody's cool? Let's do another example, but we'll do this without looking at the picture. We'll just use the equation. So here our function is 3x to the 4th minus 5x cubed minus 2x plus 2. How many zeros should we or could we find for this function? How many zeros? Four is not quite right. Not 7. 7 is less right than 4 was. 3 could happen. What else could happen?
2 and 1.
And what else?
0.
So you could write this, or instead of writing 4, you could say at most 4. But if you write just 4, Mr. Kulik's going to have to mark it wrong because there could be less than 4. Everybody's okay with that? So that's why I was like, kind of, with the 4. It's not quite right. I knew what you meant, but you have to write at most or list all the possibilities. I like at most because it feels like most of the time that's less characters than all of the possibilities. But if it's at most 1, maybe I'll write 0, 1 there. How about extrema? How many extrema could this thing have? What should it start with? So 3 isn't quite right. What do you need to say? At most 3, or you could write it as 3, 2, 1, or 0. Everybody's okay? Not tremendously difficult. You just have to remember what the theorem says. Degree is the number of zeros, extrema 1 less. And you have to use at most if you don't want to list all of the possibilities. Okay. The next feature of our polynomial graph that we're going to talk about is the end behaviors. And we talked about end behavior in general first semester. So the end behavior for a function is describing what the arrows on the graph are doing. So you always have an arrow at the left end and the right end. And if the graph is discontinuous, you might have some arrows in the middle. Polynomial functions are always continuous. So you're only going to ever have 2 end behaviors for a polynomial. So you're going to have what the left arrow is doing and what the right arrow is doing. Everybody's okay with this? To describe these end behaviors, we're going to use the limit notation that we used from first semester. So all of your limits are going to look like this, and we just have two things to fill in. For the yellow, we need to indicate whether this is the left arrow or the right arrow. To do that, we're going to use a negative infinity for left. Actually, let's write it that way. And a positive infinity for right. The green is going to be whether it's up or down. Positive infinity for up, negative infinity for down. Everybody's okay? So let's do a quick example. So I would start by typing this into my calculator and taking a quick peek. And then I'm just going to zoom standard this. All right, so let's look at the left end of our graph. Which way is the left arrow pointing? Which way is the left arrow pointing on our graph? Up or down? Down. So how do we write the left arrow points down using a limit? So we going to start here. Right? That part's always the same regardless. We have two things to fill in. What should x be approaching if we're talking about the left arrow pointing down? Should be positive infinity or negative infinity? Negative infinity, because we're looking at the left arrow. So that's where the negatives live. And then should it be pointing, this one is pointing down, so the y should be equal to positive infinity or negative infinity? Negative infinity. And the other limit was for the right arrow, so we'll use positive infinity for x approaching. And since the arrow is pointing up, this should equal positive infinity. Everybody's cool here? For polynomials, though, it's possible to figure out the end behavior without drawing the graph at all. I can just look at the function and tell. So for polynomials only, I can do this. All I need is the degree of the polynomial and the leading coefficient. So if the degree is even and the leading coefficient is positive, my left arrow is going to point up, and my right arrow points up. The way I want to think about this is just the graph of y equals x squared. Right? That's a polynomial. That's a polynomial with even degree and leading coefficient that's positive. So all polynomials with that degree are going to have that same, or with that degree and leading coefficient, we're going to have that same type of end behavior. If the degree is even but the leading coefficient is negative, what's going to happen now? Which way should the left end point, up or down? It's going to be just like y equals negative x squared, right? So both the left arrow and the right arrow point down. So far, so good. And again, like, I don't memorize this stuff. I just kind of like remember the picture. That's how I remember it. I'm a pictures guy. I don't want to like try to memorize all the notation because it's like a lot of symbols. I just would rather remember the picture, know how to write the notation from the picture. That feels like less memorizing to me. But if you're like a memorization guru, then like do what you want, man. So if the degree is odd and the leading coefficient is positive, the left end of our graph is going to point down and the right end of our graph is going to point up. What I remember here is just the graph of y equals x. That's an odd degree with a positive leading coefficient. I know exactly what y equals x looks like. You know, I've been graphing that since middle school. And if the degree is odd and the leading coefficient is negative now, what's going to happen? Well, just the ends are going to switch, right? The left end is going to point up now, and the right end is going to point down, which is just like y equals negative x. And again, I'm not memorizing the notation. I'm just memorizing the picture and know how to write the notation from the picture. You know what I mean? Like, to me, that just feels so much simpler. So if we do the same thing, excuse you. I was making a joke. Wasn't a very good one. Oops. Come on now. Stop. There we go. So again, we take the same problem from before. We notice that the degree is 3, which is odd, and the leading coefficient is 2, which is positive. So just knowing that, I know that the left limit, or the left-hand arrow, should point down, and the right-hand arrow should point up. And I'd be done. I don't have to actually graph anything. Everybody's happy there? Now, what happens if we did this first semester, what if I ask you to then support your answer with a table? So what I'm going to do then is I'm just going to pick some values of x. So for like the left limit, I want those numbers to be getting smaller and smaller and smaller. Now, there's nothing magic about the numbers negative 10, negative 100, negative 1,000. You could have picked negative 13, negative 257, negative 5,418, but like, why? I just picked these numbers because they're easy to type into my calculator, and that's what I'm going to be doing in just a second. And then for the right-hand limit, I'm going to do the same thing, except I'm going to use positive numbers. And I'm just going to use my calculator now to plug those values of x into my function. So I've already typed this equation into y1. So the easiest way to do this is to do y1 of negative 10, negative 100, negative 1,000. Where do I get y1 from again? I press vars, yvars, function y1, and then I do like parenthesis to tell it I'm plugging in negative 10, There's my answer. Now, instead of climbing back through all of those menus to get the Y1 again, I can just press second and enter, and that the calculator will just give me the last thing I typed in. So I can just go back and edit that and add a 0 to make it negative 100. And then do that again and add another 0 to make it negative 1,000. So I can write these in now. Deck. So what I'm seeing is as x goes to negative infinity, y is going to negative infinity. That supports what we wrote above. Right? Each time x gets smaller, y is getting smaller. You guys buy that? Okay. We'll do the same thing here with our positive values. So again, I'm just going to press second and enter and make this negative 1,000 into positive. Well, let's just make it positive 1,000, and we'll just go the other end down the table, right? That's easier. So again, we're seeing as x goes to positive infinity, y is going to positive infinity. That's the same thing we wrote with our limit. I think we're good. You guys feel okay doing that? Again, we did that first semester still with tables. So we should kind of remember that, especially after a little refresher. That's 13.1. So the next thing we're going to talk about is trying to find the zeros for these polynomials algebraically rather than having to graph this with our calculator. What if Mr. Kulik walked by your desk with a hammer in his hand and just smashed your calculator in front of you? How are you going to find the zeros for that polynomial now? Well, we're going to show you. So let's say we have the function f of x equals x cubed minus 6x squared minus 8x. Remember that the zeros for our function are the same as the x-intercepts, right? What is the y-coordinate for every single x-intercept? 0. So the f of x is like our y. That just needs to be 0. So this finding the zeros problem turns into a solve for x problem. And there's a typo here. This should be plus 8x, not minus 8x. So we're going to try to solve this equation. I don't know why I put the 6 in front. You should have said something when you saw me write it. Okay, we have a polynomial that's equal to 0. We want to solve this for x. My first step should be look for a greatest common factor. So if I look between x cubed, 6x squared, and 8x, what is in common, or what factor is in common with all three of those terms? X. Great. So if I factor that x out front, the polynomial I'm left with is x squared minus 6x plus 8. So that now I'm going to try to continue factoring. Notice that this is a degree 2 polynomial, otherwise known as a quadratic. How do we factor a quadratic? We need something that multiplies to give us 8 and adds to give us negative 6, I guess, so as long as the leading coefficient is 1. If the leading coefficient isn't 1, that process is a little bit more time-consuming. What are the two numbers that do that multiplication and add? Jacob, do you have it? Well, those add to give me positive 6, negative 4, and negative 2. Yeah, okay. I couldn't tell what you said that in an ambiguous way. That's why I was being coy about it. Everybody's cool? Can I factor this anymore? No. How do you know? No is correct.
I just know.
So if I look at each factor, what's the degree of each factor? 1. If all the factors are degree 1, there's no factoring possible you can do, right? It's factored as far as you can get. All right. Now that it's factored as far as I can go, I apply the zero product property. What the zero product property says, if you have a bunch of stuff multiplied together and it equals 0, at least one of those things had to be 0. So what that means is I can take each factor and set them equal to 0. Well, x equals 0, that's already a solution, right? How do I solve x minus 4 is equal to 0? Add 4 to both sides. So what do I get for the last one? X equals 2. How many zeros did I end up with? 3 zeros, right? We found exactly the 3. How many zeros could this problem have at most? 3. So I know I've got them all, right? Everybody's cool? Now, do I have to get exactly 3 zeros from a problem like this? Could I have gotten less? Yes. Let's look at an example where that happens. Okay. So again, looking for zeros. So f of x just is 0. So this is the equation I'm going to solve for. First step should be common factor, which in this case is x. Is there always have to be a common factor? No, right? Doesn't have to be one. Okay. Now that we've done that, we're going to try to factor the insides. How do the insides factor here? Yep, good. Now, does a quadratic always have to be factorable? No. This one was. We'll apply the zero product property. So we get x equals 0, x equals negative 3, and x equals negative 3. How many zeros did we get? Look carefully. 2. Because notice that negative 3 occurs twice. When that happens, we have a name for this. We say that this solution has multiplicity 2. Or multiplicity of 2 would be fine. Everybody's okay there? Notice we only really got 2 zeros, but we got 3 solutions, right? Eventually, we're going to update this theorem. So if we count our solutions the right way, we're always going to end up with n of them. One of the things we'll have to do is count our multiplicities, but there's another piece to this too that we'll cross down the road. Everybody's okay with this so far? One of the things that we're also going to be interested in is, can I look at the graph of my polynomial and tell which zeros are going to have multiplicities? So let's say that this is our graph. So this is an x-intercept, right? That's a 0. This 0 has multiplicity, or this type of x-intercept, or this type of 0 is called a straight, because you notice the graph is passing straight through the x-axis. Straights always have multiplicity of 1. If the graph of my polynomial looks like this, I have an x-intercept that hits the x-axis and bounces back the same direction it came. That type of x-intercept is called a bounce. Bounces are always going to have an even multiplicity. So the multiplicity could be 2 or 4 or 6 or 8. We don't know just from looking at the graph what it's going to be, but we know it's going to be more than 1. And the third situation kind of looks like that. So you see how if I look at one side of my x-intercept, if I poured water in there, it would kind of collect. But if I poured water here, it would just kind of run off. When the graph changes, whether it catches water or sheds water, that's called concavity. So if it catches water, that's concave up. If it sheds water, it's concave down. The graph changes concavity like that. We call that type of x-intercept a bend. And bends always have odd multiplicity greater than 1. So like 3, 5, 7. We don't know how many times, but it's at least 3. Everybody's good with that? And eventually, when we look at more complicated solving problems, this is going to be really helpful in our analysis of kind of how to go about looking for these solutions. If we can have a clue as to how many times, one of these zeros can occur. Everybody's cool? Okay. So if we go back and look at this previous problem that we just solved, x cubed plus 6x squared plus 9x. Let's just look at the graph of that right quick. What type of 0 do we see here? A bounce. And how many times did x equals negative 3 occur as a solution? 2 times. What type of x-intercept is this one? Straight. How many times was 0 appear as a solution? Just once. Everybody's cool? Okay. So just wanted to connect those two ideas. I'm going to do one story problem example, and then I have one other idea to talk about, and we're going to be done for today. Yes, sir. I sure hope so. If not, consult a physician. All right, so this says that a company wants to create a cardboard box with an open top. You guys get what I mean there? Like the recycle bin in the hallway?
Yeah.
Okay. The box needs to have a volume of 500 cubic inches, and it's created by cutting squares from each corner of a rectangular piece of cardboard in order to create tabs to fold up. So what does that mean? Oops. So it should look like this, where the shaded pieces are what we're cutting out, and the dashed line is like the perforation for where we're going to fold this up to make our box. Everybody's cool with that?
Yeah.
Okay. It says that the piece of cardboard is 26 inches by 20 inches. and we're asked to figure out what size squares should be cut from each corner in order to create the proper volume. So we're looking for the side length of that square, right? And I know squares all have the same side length. So I'm just going to label all of those sides as x. Everybody's cool with this plan? So far, so good? All right. Who remembers the volume formula for a box from geometry? It's an easy one. What's that? Length times width times height. I think you were thinking a surface area when I started hearing 2 something somethings. Okay, so let's go ahead and label our picture what our length, width, and height is. So like that dash side there would be the length. This dash side there would be the width. And like that side right there would be like my height. Can you guys all see that? Because that side we've labeled as a height gets folded up, so it's like this piece that's sticking straight up at us, right? That's our height. Can we see that? Okay. What I want to do now is I want to rewrite length, width, and height in terms of x. Let's start with length, or I'm sorry, with height, because it's the easiest. How do I write h in terms of x? X, very good, right? Because the height is just that side. We've labeled that side as x already, so h has to be the same thing as x. Everybody feel good there? Okay. What's the length going to be? So again, this is our length. Let me give you a hint. How far is this? 26. Do we want to count all of the 26? No, we don't want to count that part or that part, right? So we should write this as 26 minus 2x. Very good. You guys see that? Okay, what's the width going to be then? Oops. (20 minus 2x). Great. So we can say then we have 500 equals length times width times height. So far, so good. Now the length, the width, and the height are all polynomials, right? If I multiply polynomials together, I'm going to get another polynomial. So this is a polynomial equation. To solve a polynomial equation, what does it have to be equal? It has to equal 0. So I'm going to just start by subtracting 500 from both sides. Now, one way we could go about doing this is we could try foiling that all out, combining like terms, and trying to solve this by factoring, right? I'm not a fan of that by looking at what I have here. But what could I do instead? Well, let's think back for a moment and look at like this example here. What did I do? What was I asked to do here? I wanted to find the 0, and to find the 0, I really needed to solve an equation. So what if we flip that on its head? What if instead of solving this equation, we find the 0? What's going to be nice about that? What tool can I use to find the 0? The calculator. So let's do that. So what we'll do is we're going to type into our y equals this equation exactly as we see it, that's equal to 0. So 26 minus 2x times 20 minus 2x times x minus 500. And now I'm going to set a window here, so I have to think for a moment. X is representing a side length for a square, right? What's the smallest reasonable value for x? Zero, right? Can't have x is smaller than 0 because you can't have negative side lengths of things. So let's do that. What's going to be the biggest reasonable value for x?
You can't also have a 0.
No, but like, it's fine, right? Because it's like up to, like just has to be greater than 0. So we'll start at 0 and go bigger. You know what I'm saying? I don't want to pick 1 because I could certainly have x's be like 0.1 or something. So here's your hint. Look at this piece. What value of x would make that piece turn into a silly thing? Well, 10, right? If x is 10, 20 minus 2 times 10 is 0, and we know we don't want to have a dimension 0. And if it's bigger than 10, it's going to be negative. That's rough. So let's make 10 our x max. That'll be the biggest x we can get. Our y is going to be like a volume. So again, volumes have to be positive. So let's make our y min 0. And our y max is probably going to be potentially quite big because it's going to be, like this thing can be at least 500. The volume could be bigger than that depending on the dimensions we pick. So I'm going to pick my y max to just be like 500. I'm just kind of taking a guess at that. And then I'm going to graph. Ooh, that looks okay. So how many solutions is this equation going to have? 2, because we're seeing 2 x-intercepts, right? Let's use our calculator to find them. Second, trace. 0, command. Now I'm going to find this solution first. So notice that it's asking for a left bound, and I can't really see where this is, right? But the calculator tells me the location of my cursor. So I'm just going to keep pressing left until I see that y value turn negative. Because at that point, I know I'm past my x-intercept. So I'm just going to kind of like cruise here to the left till I see a negative number. Oh, that looks good. That's negative. I'll press enter and then cruise back to the right just till I get a positive number. Press enter. Guess doesn't matter. So I get about 1.20. And then I'll do the same thing for the other one. I'm going to skip doing it by hand and showing it. I trust that you guys can use the X or the 0 command on your calculator because we just practiced it like literally a half an hour ago. But the other answer should be about 702. So that's it. Is that okay? Now, what I just showed you, for those of you that are still having ACTs to take, this is a lovely, lovely method. If you're taking a multiple choice test that nobody cares about the work you show, if you run into an equation that you don't know how to solve, just get everything onto one side, graph it on your calculator, find the x-intercepts. Unless they want imaginary solutions, you're good. That's really nice for those of you that still have potential standardized tests to take. That is a super effective method to be able to solve something that you really have no idea how to solve. All right, one more topic in 13.3. And the topic that I want to talk about here is polynomial division. So let's say that we have, let's do this numerically first. Let's say we have 127 over 13, and I ask for this as a mixed number. So if we go back to middle school, we write this as a division problem. We go, okay, how many times does 13 go into 12? Well, 0, so we'll move back out. How many times does 13 go into 127? I think 9. So 9 times 13 is 117. And then I subtract down. So I'd say that the division problem here is 9 remainder 10, which tells me that this mixed number is going to be the quotient plus my remainder over my divisor. So it's 9 and 10/13 will be the mixed number. We can do the same thing with polynomials. So if I take some polynomial p of x and divide it by d of x, I can write that as a quotient plus a remainder over the divisor. Let's do an example of that process. This is something you would have done last year in your Algebra 2 class, or maybe are currently doing in your Algebra 2 class if you're co-seated. So let's draw our division bar. What's going to go out here? X squared minus 3. Okay. And what's going to go in here? The numerator, right? Now, before I begin, I want to look at both my numerator and my denominator and check to see if there's any skipped terms. What do we skip here? An x. So I'm actually going to write this as x squared plus 0x minus 3. I don't want to have any skipped terms. I'm just going to put a 0 and then whatever needs to be there for the skip, so everything lines up nicely for me. All right. Now that I've done this, I'm going to ask myself the question, what times x squared gives me 2x cubed? 2x. So I'm going to write my 2x, and then I'm going to multiply it by the entire divisor and write that below. And then we'll subtract down. Now, in my experience, the number one place that students make mistakes when doing this kind of a problem is they forget to subtract each term. What I'm going to tell you is that you should distribute the negative and just turn this into an addition problem. So that's what I'm going to do here if my eraser wants to do something. So I distribute the negative. That becomes negative 2x. That becomes negative 0. And that becomes positive 6x. Everybody's good? Now I'm just going to add straight down. 2x cubed plus a negative 2x cubed is 0. Negative 4x squared minus 0x squared is just negative 4x squared. 5x plus 6x is 11x. And then I'll bring down whatever I haven't dealt with yet. And then I'm going to repeat and say, what times x squared gives me negative 4x squared. So my new leading coefficient. Negative 4. Everybody agree? I'm going to distribute that negative 4. And then subtract down. But I'm not actually going to do this as a subtraction problem. What am I going to do? Distribute that negative. Negative 4x squared plus 4x squared is 0. 11x plus or minus 0x is 11x. And then 1 minus 12 is negative 11. I know that's my remainder because the degree of what's left is smaller than the degree of my divisor. Whenever I see that, I know that I'm done at that point. So what can I say here? I can say that 2x cubed minus 4x squared plus 5x plus 1 divided by x squared minus 3 is equal to the quotient plus the remainder over the divisor. Let me just color code that a little bit for us. Everybody's okay? You remember doing this last year? Now, there's a second way to do polynomial division. That's called synthetic division, right? Which one was easier to do? Synthetic division. Well, if that's easier to do, Mr. Kulik, why don't you show us that first? What's the drawback with synthetic division? There is a drawback. The drawback is you can't do synthetic division for every division problem. To do synthetic division, the divisor has to have degree 1 and leading coefficient 1. If you don't have those two things, you should do long division. Here, we have those two things, so let's set this up as a synthetic division problem. What goes on the outside here? Negative 3, great. What you do is you take this, set it equal to 0 and solve. That solution goes out here. What goes inside? Good. What do you have to be careful about on this part? If there's no 16x here, what would you have to include? You'd have to put a 0 there, right? You have to have those. It is unrecoverable if you make that mistake and don't include the zeros. Okay. So the way this begins, we drop the 6 down. We multiply the number on the outside to the number on the bottom, write it in the next open spot, and then add down. And then we just keep repeating that process until we've filled in all of our spots. You guys remember doing that? Now, these numbers at the bottom somehow need to tell me what the result of this division is. So the way we interpret these numbers, we always start on the far right. The rightmost number is the remainder. The next is our constant term, our degree 0 term. The next is the coefficient on our degree 1 term. The next number is the coefficient on our degree 2 term, and we keep going, adding 1 degree as we move to the left. Everybody's cool? So this problem, what we could say is that this equals 6x squared plus 7x minus 5 plus my remainder over the divisor. Do I really need that? No, I don't. What does it mean if I have a 0 remainder? So that tells me that x plus 3 is a factor of 6x cubed plus 25x squared plus 16x minus 15. And we'll use this as a foundational idea for what we're going to look at next time. But that's as much as I want to do today. You guys cool? All right. For homework, you guys should be able to do 1 through 12 and then 15 to 19. When is that going to be due? Not this Sunday, because we don't meet again before Sunday. It'll be due next Sunday. What's due this Sunday? Absolutely nothing. Who's excited about that?
Me. But this guy right here in blue.
Good. So if you're behind on some stuff, like you got some missings, rather than spending your time doing new math homework this weekend, maybe catch up on a couple of missings, you know?
It's a good idea, actually.
It is a good idea. It is. All right. Any questions for me from you guys? No. Okay. I'm done. Have a great day.